Welcome to the final lecture on algorithms. We're going to briefly wrap up by talking a little bit about memory complexity. We've already discussed this a bit in analyzing our Fibonacci sequence memoization, where we were able to improve the time complexity by carrying around this dictionary D, which had an entry for each number n between 0 and the nth Fibonacci number we wanted to calculate. So if we wanted to calculate the 25th Fibonacci number, we would end up with 25 entries in our dictionary D. So the memory complexity of that memoized solution was order n. The data structure, the dictionary, grew linearly with n. We would have one new entry in the dictionary for each increase in n. Just to provide a simpler example for comparison, we can consider two different sum functions for computing sums between the numbers 0 and n. One in which we essentially use a list. And here so I need to actually put list around range here, because range is a generator, so we're not storing the numbers in memory. But if I put them in a list, then we create a container in memory that stores all the numbers 0 through n. So here we have a data structure with all the numbers 0 through n, and we simply return the sum of that list. So there's a built-in sum function in Python, and we can just apply that to our list. So this has a memory complexity of n, because if we have n coming in as input here, we're going to have n numbers in our list. We could also have a sum iter function that receives n, and we simply iterate a variable number up to n and compute a running sum, adding in each number as we increment it. And these return the same results. They are computationally equivalent, but here I use a constant amount of memory. I have two variables, number and sum. They're both integers, and no matter how large n is, I'm using the same amount of memory, just two integers. Meanwhile, here, as n gets bigger, I use a larger and larger list. So my data structure grows linearly in n. So just like we analyze time complexity, we'll often want to analyze memory complexity. And there are some tricks. Earlier, I mentioned when analyzing time complexity, one thing we would be on the lookout for is nested for loops. So for each for loop, we essentially end up with a power of n. So if I have some string with n characters, we might say for character in string, and then we might say for, and just to give an example here, we might say for we might enumerate that string, and then we might say for character in string I until the end. Maybe we're doing something where we're comparing different letters in this string, and we're iterating over the string twice. Here we're iterating over the string in its totality, and then here we're iterating over a substring each time our iteration over the string advances. So in general, we're iterating over of something of roughly size n, and here we have n steps in the outer loop. So we're taking roughly n steps for each step in this n-step loop. So this gives us, this doesn't actually need to be executable code, I'm just illustrating a point. This would give us n times something roughly n sized. So this would be order n squared time complexity. So this is like sort of a trick for figuring out time complexity. If we have nested for loops, we get a power of n for each layer in the for loop. So if there were 3 for loops, we'd have n cubed. For a single for loop, we're probably looking at something that's order n. If we have a tree structure like we saw with the Fibonacci sequence, we might be looking at something logarithmic. If we're concerned about just stepping down steps in the tree, we saw that with our binary search. We would be dividing the list in half each time. So that gave us a factor of log n. Or yeah, so those are the big ones. Powers of n and log or exponential. Exponential is if we need to do every element in a tree structure. Log n is if we can construct a tree structure and then walk down a single branch, or like level by level, because there will be log n levels in a tree with n elements. Or in a tree with n levels, there will be exponential of n elements. Similarly, for memory complexity, we can usually just look at the dimensions of the data structure we're constructing. If we have a list with things up to n elements, this is order n. If we have something like a list of lists, and there's n of them, then this is order n squared in size. We might have a dictionary that similarly could be anything depending on how we construct our keys. So for the Fibonacci sequence, we had something like this. So this was also order n in size. We had one key for each element in the dictionary. We could have a situation where we have composite keys. Where we have maybe two different ways of generating these two different elements of the key. And then we would have, if there's roughly n letters and n numbers coming in here, then we have n times n keys. So again, this would be order n in size. Or n squared in size, sorry. N times n squared keys. But we might deal with all kinds of different data structures, and the key is to look at their shape, or the shape, how they're structured, and consider how many entries there should be in terms of how many inputs we have, or in terms of our input size. So that's a brief primer on memory complexity and analyzing that. To conclude, now that we've talked a little bit about trade-offs between time complexity and memory complexity, and we've talked a bit about how to use data structures to speed up certain tasks like search, or to help us memoize results in a recursive call stack, I want to talk a little bit more about the relationship between data structures and certain algorithms. So I've mentioned this computer science book several times called Problem Solving with Algorithms and Data Structures. And it introduces a number of data structures in different parts of the book. For example, heaps, which it relates to binary search. And let's see here. It also talks about depth-first search or breadth-first search, methods of searching tree or networks, tree-like data structures or networks. And when it talks about these, it relates them back to a data structure, or data structures called a stack and a queue, which it talks about back in the basic data structures chapter. So there are, you may have also heard me say, as I was talking about recursion, a call stack. So certain algorithms are often linked to particular data structures in a natural way. And when we're writing a new algorithm, we want to often think about if we're going to use data structures in that algorithm, and if so, what kind of structure should they be? What data structure ought we use? So just to give a small example, earlier we talked about binary search. And we mentioned that binary search, if we already have a sorted data structure, can be done in log n time instead of linear time. Now, I said if we start with a sorted data structure and we expect to do search a bunch of times, it may be worth sorting the data structure in the first place, paying an n log n time price, if we're going to search more than n times, because we'll pay log n each time we search, and eventually, searching n times, we end up with n log n for our searches, plus n log n for the sorting. Whereas if we had just left it as an unsorted list, we would be looking at n searches that each take order n times, so n squared. And n squared is much larger than n log n. Now, in this situation, that's fine, but if I add to the data structure, if I add to my list, it's in general not going to be sorted anymore. So, if I start with a sorted data structure, as soon as I add something, I have to pay an n log n price to sort it again. And that's not very, that's not a price we want to pay if we're updating our list a lot throughout the execution of the program. But, for example, in this situation, we could use a heap. So a heap is a list that's sorted in a special way. It's not actually stored in sorted order. It's stored in a particular order that allows us to add elements to the heap in such a way that we can read out the elements very quickly in sorted order. So they have a particular relationship in their positions that's where you can, even though it's not sorted largest to smallest or smallest to largest, they are sorted in a order. And this order is specially designed to allow us to quickly add new elements to the list in sorted order. And it's really fast to add an element to a heap in sorted order. It only takes log n time. So now, if we're maintaining a heap instead of a list, if we need to add new elements, we don't need to pay an n log n price to resort the list. We can add new elements in sorted order with a log n price in time. So I don't expect you to become experts on heaps or to have followed all of this discussion necessarily of why we might choose a heap exactly, but I hope that this discussion has impressed upon you that when we're writing code, we often want to think carefully about our options in terms of how we store data, if we should store data, and how that might impact how long it takes our functions to run, as well as what memory resources we're spending to accomplish any efficiency improvements in time. So as exercises, after the conclusion of this lecture, I'm going to leave you with these two questions. Explain why sorting and then using binary search is slower than just searching a single time. And then using the binary search function that we defined previously and analyzed in the first lecture of this series, use the principles of this function instead of to perform search, to perform element insertion in a list. So I'll leave this lecture here, and we'll be moving to a new notebook in the next lecture.